The MindWalks program is underwritten by the Thomas E. and Mary Kathryn Eltzroth Fund and supported by the Central Coast State Parks Association. So Scott's here with us today. Scott Johnston is a professor of geology at California Polytechnic State University, who combines field structural geology, geochronology, and geochemistry to study the tectonic processes associated with the mountain building at convergent margins. He received a MS degree from Stanford University, studying the evolution of faults near Great Basin National Park, and a PhD from the University of California, Santa Barbara, studying the exhumation of rocks from 60 kilometers below the Earth's surface during the collapse of a Himalayan scale mountain range that formed in Norway over 400 million years ago. Since arriving at Cal Poly, Johnston has worked with students studying the evolution of mountains in East Greenland, Ontario, Canada, the Sierra Nevada, and in Big Sur. His hobbies include surfing, skiing, mountaineering, and bluegrass music. Thanks so much, Scott, and I'll let you take it away.
All right. Hello, everybody. I'm going to see if I can share my screen here. Okay, so yeah, I'm going to be talking about the Morro-Islay Volcanic chain and how they formed, and also some of the rocks in which they are hosted within. So some of the other local geology of San Luis Obispo area. But more than anything, I'm kind of here to answer your questions. So so please interrupt me if you've got any questions. And I love to talk. So hopefully I can help you do that. I've got my pen here. I've got the big board behind me, so I love to draw. Yeah, just please ask me questions. Don't hesitate to interrupt me. Okay, so here we are. This is a picture from the Cuesta Ridge area, and kind of looking out across foggy San Luis Obispo. Beautiful morning though. Here's Bishop's Peak, Cerro Romaldo, and then out here is Hollister Peak. This is Cerro San Luis. So as you guys probably all know, these are volcanic rocks. These are little volcanoes. So how do they form, and what are they doing here? So my sort of talk outline is going to follow this sort of organization, I guess. First, I'm going to talk about what the morros are composed of and sort of describe the rocks and look at them a little bit of detail. I'm looking at the minerals and the textures in the rocks themselves, and then also describe some of their relationships with the rocks around them, what they're intruding through. I'm going to talk a little bit about the age of the rocks, not just the morros, but also the rocks which they're going through. And then I'm going to talk about how all of these rocks formed. And in particular, I'm going to talk about the volcanic setting. Because there's volcanoes and there's volcanoes. There's all sorts of different types of volcanoes, and they all form in different ways. And it turns out that this is all sort of closely related to the tectonic evolution of the Central California coast. So we'll sort of finish off with how the Morro-Islay volcanic chain fits into the evolution and the geologic sort of formation of where we live. Okay, so I'm going to start off this. This is what we call a geologic map, right? And so all these different colors mean different types of rocks. What I've highlighted here are the actual volcanic rocks that are associated with the Morro-Islay volcanic chain. Right? So these are a series of rocks. They all look pretty similar to each other. There's subtle differences, and people have mapped very small differences in different areas. But in general, they're all similar. So people think of them as forming, around the same time and through a similar process. You'll also notice that they form this really nice sort of linear trend that stretches from Morro Rock all the way to the southeast here at Islay Peak. Okay, so if we look at these rocks in detail, this is the general sort of look that they have. And they're kind of this sort of gray rock. And if you're standing far away, you might say a monotonous gray rock. But when you look up close, you start to see that there's actually quite a bit of variability. So this is a type of rock, it's called dacite. There are other types of rocks, again, in the Morro-Islay Volcanic chain, but the majority of it is dacite. And so when we look closely at this rock, this is kind of what we see. And each of these little areas are different types of minerals. Essentially, they're crystals. And so these little white spots, those are plagioclase feldspar. Feldspar is probably the most common mineral on continental crust or within continental crust. And if you go to the Sierra Nevada, feldspar, plagioclase feldspar is what gives the granites in the Sierras that sort of really nice bright or light color. In addition to the plagioclase feldspar, there are also these little gray areas, and this is quartz. So here's a quartz crystal here, there's another quartz crystal down here. So there's quartz scattered throughout this rock as well. So it's not just plagioclase feldspar, there's a fair amount of quartz. And when we're looking at minerals, we differentiate the minerals in different ways. One obviously is with color. The plagioclase tends to be this sort of lighter or white color. Quartz tends to be gray or sort of more translucent. And in addition, you can't see it unfortunately in this picture, but when you move the rock around in the sunlight, they'll flash back at you. These are crystals, and the plagioclase feldspar in particular has these really nice faces on which the crystals break. They're called cleavage planes. The rock cleaves along perfectly smooth planes. The quartz doesn't do that. It breaks more like window glass. So we use different sorts of properties to identify the minerals. Okay, so here we can see plagioclase, we can see quartz. There's these little black minerals, and these are biotite mica. And in cross-section, they form this really nice sort of hexagonal shape. They also have a lot of iron in them, so they kind of rust, and you'll see them kind of bronze in color. They also have very nice cleavage planes, and they'll flash back at you when you move this thing around in the light. The other dark mineral is this sort of duller black color, and that's hornblende. Okay, so there's these different crystals in here, and they're all different minerals. And when you see a rock like this, with these sort of assemblage of minerals, is called dacite. But the last thing that I haven't talked about yet is all of this fine-grained material that all of these other larger crystals are floating in. So this is what we call microcrystalline ground mass. Okay, so these are basically a bunch of very, very fine crystals that you can't see with your naked eye. And so because they're so small and oriented in different directions, that's what gives them this sort of gray color. If we were to look at this rock, like this next picture, through a microscope, these are these large plagioclase crystals. And in this one, you can actually see chemical zoning from the core to the rim. You can see the sort of rinds here, like layers of an onion almost, where the crystal actually changes chemical composition subtly from the core to the rim. And you can also see, these are called twins, where there's mistakes in the crystal lattice that cause it to have light pass through it in different directions. This is a nice big biotite crystal, and this is the ground mass. So you can see here, when you look at this, that these are just a bunch of teeny little microcrystals. And for the most part, they're the same composition as the larger crystals. There's going to be mostly plagioclase with some quartz and some biotite, right? So this is what this rock looks like. This is what dacite looks like. And when geologists think about these sorts of minerals, and they also think about the textures, they can start to learn stuff about the way that this rock formed. So one of the things that we think about when we look at particularly texture, and with igneous rocks, so igneous rocks are rocks that cooled from a magma. So this used to be a molten rock, basically a liquid rock. And as it cooled down, well, it essentially froze and started to form crystals. And as these rocks crystallize, and as they cool down, the little elements that are moving around through the liquid, kind of moving around like this, if they've got enough time they like to get into nice big crystals, and they like to form nice big crystals. So that's how this big plagioclase feldspar formed, and that's how this big biotite formed. They were slow forming crystals. So probably what happened with this magma is that it slowly started to cool down, forming these large crystals. And then this magma, with the crystals floating in it still, erupted to the surface. Of course, when it got to the surface, it cooled very quickly, and that's when the rest of the ground mass forms. So when we see rocks like this one that have coarse and fine grains to them, we think that this rock probably cooled slowly, initially, deep in the earth somewhere, and then erupted and cooled quickly. And ultimately, this rock cooled very near the surface of the earth. Otherwise, it wouldn't have cooled so quickly. So that's why we call this a volcanic rock, because it's an igneous rock that cooled from a magma, and that magma cooled within the volcano itself, not deep under the earth where it would have cooled slowly. The other thing that geologists do when they look at these rocks is they think about the composition of the rock. Okay, so we look at the minerals, and I mentioned that there's chemical zoning in this plagioclase feldspar. And obviously the plagioclase feldspar has different elements in it than the plagioclase. That's why it has, these different colors, different properties. There's actually different amounts of iron and magnesium and calcium and sodium in each of these minerals. Right, so the relative abundance of these different minerals sort of defines the bulk chemical composition of this rock. So it turns out that dacite is something that we call felsic. It generally means less iron and magnesium and more silicon and oxygen. And in general, dacite is very similar to like the granites that you would see in the Sierra Nevada. The bulk composition is nearly the same as what you'd see in Yosemite. The minerals, the elements are the same. The only difference is the size of the crystals. Okay, so this is in general what continental crust looks like. It's very different from oceanic crust that has more iron and magnesium and less silicon and oxygen. Okay, so another thing we can think about here when we look at this map here is that the Morro-Islay volcanic chain is intruding through all of these sort of purples and sort of reddish hues. And so what that tells us is that these purples and reds were here, or whatever the color this is, these purples and blues and darker reds were here before the Morro-Islay volcanic chain popped through them. All right, so this stuff is something that we call the Franciscan complex. So this is another important rock formation in the central California coast. So I'm going to talk about it for a minute here. So this is a Google Earth image. So taken from Google Earth, and here you can see Bishop's Peak on all the way out towards Morro Bay. If you've walked on the Felsman Loop here, one thing you might have noticed is that there's some very different looking rocks right next to this water tower. This is part of the Franciscan complex. And so if we just zoomed in on the Franciscan complex, at least this one outcrop right here, what you'd see is something like this. This is actually, these are deep marine, so deep ocean sediments, and it's inner layers of chert. And these are actually billions and billions of little teeny microscopic radiolarians, so essentially plankton that piled up on the bottom of the ocean floor, interlayered with mud. And so there's a big blob of, or block of chert and mud at this location. And when you take a step back and look at a lot of sort of areas where the Franciscan complex is found, this is sort of a typical sort of relationship where you see sort of grassy hills with not many rocks, and then bonk, there's these big blocks that are sticking out of it. And these grassy areas are generally areas where the rock is relatively soft and erodes quickly, and these are areas where the rock is more resistant to erosion, and so they stick out as these big blocks. So let's take a little look here, and when we start to look at these blocks, it turns out they have all sorts of different compositions. So this is another block. You'll notice that it looks a lot different from those cherts. This is not a sedimentary rock. This is actually volcanic rock. And this is a volcanic rock that formed at a mid-ocean ridge. So it has a different composition than the Morro-Islay volcanic chain. And so these are pillow basalts. And you can see them on the beach in Cayucas. You can also see them in Avila and all throughout the Franciscan complex. But it has this sort of characteristic sort of bulbous or rounded off shape where big blobs of magma get erupted and get in contact with the seafloor, with the ocean, and they form these sort of what geologists call pillows. Not the softest pillows. Okay, so in addition to the pillow basalts, if you go up to the San Simeon area and look at some of the beach outcrops, you can see all sorts of other types of rocks. And in addition, because these are the beach outcrops, you don't have to deal with the pesky, dirt and grass or anything like that. You just get to see the rocks. So here we can actually see the mud that is enclosing these larger blocks. And so these are sandstone blocks, a sedimentary rock that probably formed in some sort of near beach environment. Here's another picture where there's this green rock. It's called greenstone, right next to this blue rock, which is surprisingly blue, and it's called blue schist. Right. So the point here is that the Franciscan complex is a whole bunch of different types of rocks. It's what we call a melange, which is French for mixture. Sometimes I like to call the Franciscan complex the French shish kebab. So it's like a shish kebab. The shish kebab has like some onions next to a pepper, next to like some meat, it's a whole bunch of different things that are all mixed together, which is exactly what the Franciscan complex is. It's a whole bunch of different types of rocks that are all mixed together in this mudstone sort of matrix. Okay, so that's what we have here. We've got the morros, that are these volcanic rocks that cooled slowly, then quickly, that are intruding and popping up through this older Franciscan complex. That's a mixture of a whole bunch of different types of rocks. Okay, so the next thing that a geologist might want to do is figure out, well, these are different types of rocks. What's the relative age of these rocks? And the very simple answer to that is, the morros could not have intruded through this Franciscan complex if the Franciscan complex wasn't there. And so we can say that the morros are younger. We can't say necessarily how much younger they are, but we know that they are younger than the Franciscan complex. So that's relative. It's just putting different types of rocks in relative order of events. But we can do better than that. So we can also do what we call absolute geochronology, which is different in the sense that now, instead of just putting different rocks in relative order, which ones are older and which ones are younger, we're going to actually try to figure out how old each of these different rocks are. And there's a lot of different methods for doing this, but they all involve basically radioactive decay and measuring different isotopes. One of the most common minerals that people use in rocks to date them this way is a mineral called zircon. So these are little teeny zircon crystals. And again, this is through, in this case, this is just a standard reflecting microscope. And these are about, 100 microns in diameter. So they're teeny little crystals, but they're relatively common. You find them in most rocks that at least are associated with continental crust. So that makes them useful. So even though they're not big, they're relatively common. You can find them in most rocks. And the other thing that makes zircon particularly useful is it concentrates the element uranium. And when I say concentrate, I'm not talking really high concentrations, but I'm talking maybe 100 parts per million or 500 parts per million at the most. And that doesn't mean that any rock you pick up is going to have a ton of uranium in it, because there's not that much zircon in that rock. But there's a little bit of zircon. If you get those zircon crystals out, they've concentrated the uranium. And as you know, uranium is radioactive. And so the uranium decays to lead. And the lead is not radioactive. So the moment that these zircon crystals form, the uranium that is concentrated within their crystalline structure starts to decay to lead. And the moment that this crystal forms, there's almost no lead in it. So any lead that is generated is coming from the uranium. So by counting up the uranium and the lead atoms in this crystal, then we can figure out how old each of these crystals is. So the next thing that we do is we have to count atoms, which is not particularly easy, but it has gotten easier. So this is actually something that my students and I do every year. And we go down to a lab at UCSB. And they've got a bunch of fancy instruments in this lab. And so what we do is we take those zircon crystals and we polish them and we put them into this instrument right here, which is a laser. And then using this monitor, and this is the same monitor here, we can sort of zoom in on the crystals, and then we can place little spots on the crystals where we want to sort of micro sample that zircon crystal. Right, so what the laser does is it micro samples the crystal by blasting away at it, and it gets a little bit of that zircon crystal gets essentially ablated and carried by a gas into this instrument right here. And this is a mass spectrometer. So basically what it's designed to do is count atoms. And the atoms are accelerated through this instrument, and the heavier atoms, because they're heavier, they wrap around this magnet and they end up over here. And the lighter atoms, because they're lighter, they get bent more by the magnet and they end up over here. And that way we can count the uranium and the lead atoms. It's a pretty fancy process, and it took a long time for people to develop these instruments. But now that the instruments have been developed, this is a pretty routine process as well. And there are labs all over the country that do this routinely. Okay, so this is Melissa Beck. She was a student that I had at Cal Poly maybe 10 years ago. And so she got really interested in the morros, and she wanted to do some modern geochronology on them. So she extracted zircons from the dacite at Cerro Cabrillo and the dacite at Islay Peak. And these rocks, at least within air, are identical in age. They're about 26.7 plus or minus 100,000 years. So 26.7 million years plus or minus 100,000. So that's how old the morros are. There you have it. The previous
Scott,
estimates.
we have a question.
Yeah.
Sorry.
Great.
So yeah, let's see. It says, how do you separate the zircon crystals from the larger rock?
Right. Good question. And that's a process that we do in a relatively rudimentary way. This is all really fancy, but the way we get the zircon crystals out is the first step is we take the rock and we crush the rock into basically sand. And so all of the crystals, whether they're quartz, feldspar, or zircon, are separated from each other. And then we use a series of density and magnetic separations. So the first thing we do is we use like a gold pan, and the gold pan gets rid of the majority of the quartz and the feldspar. Zircon ends up being very dense. The next step is we use some weak magnets to get some of the more magnetic minerals, because some minerals have a lot of iron and magnesium and things, or iron in them. They tend to be more magnetic. And the next, so that gets rid of some of the heavier, some of the other heavy minerals. The final step is we use something called lithium metatungstate. It's basically a very dense liquid. So this liquid has a density of about 2.9 grams per centimeter cubed, which means that if you put quartz crystals into lithium metatungstate, they float. If you put granite into this liquid, it'll float. Of course, zircon has a density that's about twice that, so it sinks. There's a few other dense minerals that we were able to essentially get rid of using an electromagnet, so a really powerful magnet. And so then basically what's left is the zircon crystals with usually a little bit of other stuff, and then we hand pick the zircon crystals using a microscope. So that's sort of brute force, and then this is where all the fancy business comes in. Okay, so the morros are 26.7 million years old. What about the Franciscan complex? And this is work that a colleague of mine has been doing and published on a couple of years ago. And because the Franciscan complex has a bunch of different types of rocks in it, they looked at the sandstones and the mudstones that all the other rocks are included within, and figured that they're the youngest. Basically a relative dating technique. And then they looked at the zircon crystals in those sandstones, and the youngest crystals that they could find were between 81 and 98 million years old. So the idea here is that the Franciscan complex is around that age. This is called what we call something called a maximum depositional age. And where we have maximum depositional ages together with chronostratigraphy through inner layers of volcanic tuffs, these maximum depositional ages tend to be pretty close in age to the actual age of the rock. Okay, so the Franciscan complex is, what, 50 million years older than the morros that intruded within them. Okay, so now what I'm going to sort of change gears here and start thinking about how these different rocks formed. Okay, so the first thing I want to start off is with the Franciscan complex and how the Franciscan complex formed, how all these different types of rocks kind of got mixed together. And so to understand the Franciscan complex, I'm going to throw this diagram up here. This is a model of a typical convergent boundary. So when I say convergent boundary, now I'm talking about plate tectonics. So I'm talking about really big scale processes. And this is oceanic crust here in blue. And this is continental crust here in green. In fact, this is a Google Earth map of the South American margin. And so what happens at a convergent boundary is because the oceanic crust has more iron and magnesium in it, it's denser, and because these two different tectonic plates are colliding, this oceanic crust sinks. Right, so sometimes these convergent boundaries are called subduction zones. And of course, as they move together, all of this oceanic material that is slowly piling up on the ocean crust, as well as material is coming from the continent and piling up down in this area, it forms a little pile here, and it slowly gets scraped off by the continental crust. And it forms what we call an accretionary complex. So another way to think about this is with a simple little cartoon here. So this is after a snowfall, and here's some pavement, and here's a snow shovel. So when you push the shovel through the snow, all of this material, which is kind of coming into the shovel, gets piled up in what we call a wedge. So we can kind of watch this here, and the shovel piles this wedge like this. And as the shovel moves forward, which is kind of like thinking about more oceanic crust getting pulled into the subduction zone, more and more material piles up in that wedge. Okay, so when I reverse this, one thing you'll notice is that big blocks that end up here, they roll down towards the front. There's one right there. You can see this crystal, this big block of snow starts to roll down towards the front. So that's one way that these different types of rocks can get mixed up. It's what we call a sedimentary melange. The other way that the rocks can get mixed up in this wedge is at the base, where these different layers are getting scraped up and kind of mixed together, imbricated together. Okay, so if we look at a more complex model of just the accretionary complex here. So here's our convergent boundary with the subducting oceanic crust. This is this material that's getting scraped up. And it doesn't just all get scraped up at once. As it's getting scraped up, there's a bunch of mixing going on, and we call these tectonic melanges. At the same time, as this wedge grows in elevation, it starts to roll down, and parts of it get reincorporated at the front, and they can become sedimentary melanges. So as these wedges grow over millions and millions of years, different rocks of different ages are all getting mixed up together in this accretionary complex. And that's what happened in California. It's called the Franciscan complex, not because it's along the coast of California where the Franciscan monks traveled. Right, so we see this very characteristic melange all up and down the coast of California, from Northern California all the way down, past Santa Barbara or into the Santa Barbara area. Okay, so then what about the volcanic rocks that are popping up through this accretionary complex, through the Franciscan complex? Okay, so I'm going to go back to this model here. And this is where I'm going to start talking a little bit about how magma forms in the first place and how volcanoes form and how and why they form. So I think one sort of interesting misconception that people have about our Earth is that if you go down deep enough, it just turns liquid, which is true. If you get all the way down to the core, you get to a solid or a liquid portion of the core. But that's not for like 5,000 kilometers. So before that, there's this area that's called the mantle. Right? The crust is at the surface here in the pink and the blue. And below that, there's this stuff called the mantle. And it's solid rock. Right? So if we want to make volcanoes, the first thing you have to do is you have to melt rock, right? You've got to find a way to melt the rock. Okay, so in this next slide, I've shown some of the main ways that people learn about in introductory geology about how rocks get melted in the first place to form the magma that eventually rises to the surface to make the volcano. In general, there's sort of two ways that this can happen. The first and probably most common way that this happens is what we see at mid-ocean ridges and at hotspots. In both of these types of places, rocks from the mantle are being drawn or are moving towards the surface. They're moving towards the surface because they're being pulled up in the case of mid-ocean ridge, or because they're hotter and less dense in the case of a hotspot. And so as this material rises towards the surface, it decompresses. There's less pressure at the surface than there is deep in the earth. And if there's less pressure holding the rocks together, well, the atoms can move around a little bit more, and eventually, without enough pressure, they just melt. Okay, so that's one way. We call this decompression melting. Right, so the reason we have lava forming pillow basalts at mid-ocean ridges, and the reason we have lava forming pillow basalts and similar things like at Hawaii, like hotspots, is because this rock down here in the mantle is decompressing and melting. The other way that magma can form is what we find in subduction zones. And as the oceanic crust gets buried, as it sinks into the mantle here, it ends up releasing water. This is not the type of water that you typically think about. This is not like water that you could drink. Instead, the water that's being released is actually coming from the crystals themselves. You may remember that crystal biotite I showed you. Biotite, by weight, is like 3 weight % hydrogen and oxygen, or excuse me, not 3 weight %, it's 7 weight %. Hornblende is 3 weight % hydrogen and oxygen, which means that there's water actually locked in the crystal structure. And as those crystals get buried, they heat up, and that water gets released. The biotite turns into something else. The hornblende turns into something else. And by adding water into this mantle area, that actually lowers the melting temperature of these rocks, and they start to melt and rise towards the surface, and they create what we call a volcanic arc. Okay, so at the same time that the Franciscan complex was forming at the convergent boundary, the Sierra Nevada was forming new granites and volcanic rocks. through this subduction zone process. At the same time, there was a mid-ocean ridge off the coast of California that was forming new oceanic crust. And you'll notice that in this picture, there's no real way to make volcanoes in the accretionary complex itself. At least it's not shown on this diagram. Maybe a hotspot could be coming up in this area, but hotspots create a tremendous amount of material. Think about Hawaii and the size of Hawaii and the Hawaiian Islands, and compare that to the Morro-Islay Volcanic chain. Also, when you think about Hawaii, there's a range of ages, and the Morro-Islay Volcanic chain is all roughly the same age. So the hotspot doesn't really fit the model for the morros that are here in the accretionary complex. Right, so I guess what I'm getting at here is that what you learn in geology, introductory geology, is about these different sorts of settings where volcanoes form, and none of them actually fit the Morro-Islay Volcanic chain because of where it's located and also the types of rocks that it is. Okay, so then how did they form? So this is where we get to this idea of a slab window. And this is a map that shows what the sort of the west coast of North America looked like about 40 million years ago. And this right here is this mid-ocean ridge where new oceanic crust is forming. And then this right here is the convergent boundary. So at this time, there's the sinking oceanic crust, and we call that the Farallon Plate, which is sinking beneath North America. And it was also forming the Sierra Nevada here, as well as like the peninsula ranges, the granites that you see in the peninsula ranges, on up through the Cascades as well. So if we just look at this video here and we kind of go forward in time, one thing you'll notice is that the mid-ocean ridge was not stationary with respect to North America. What I mean by that, if we start 40 million years ago, you can see the mid-ocean ridge is well off the coast. But as time goes on, it gets closer and closer and closer until about 30 million years ago. Here we are like 27 million years ago. Now, that mid-ocean ridge has impacted or has basically been overrun by the North American continent. Okay, so this is sort of the tectonic setting when the morros formed. Okay, so let's look at that in a cross section. Okay, so what I've done here is I've basically shown this mid-ocean ridge off the coast here, and in this section, it's overrun by the subduction zone. If we look at the cross section right here, it's basically business as usual. Mid-ocean ridge is a little bit closer to the continent, but there's still a subducting slab, basically a subducting piece of oceanic crust that we call a slab that's releasing water and forming a volcanic arc. There's a mid-ocean ridge with magmatic rocks and volcanic action at the mid-ocean ridge, but there's still no volcanic activity in the accretionary complex. Okay, but if we, instead of drawing the cross-section here, what if we draw the cross-section a little bit farther to the north here? In this area, there's no more mid-ocean ridge. The mid-ocean ridge has essentially been subducted. All right, so here's this old slab that it's still sinking into the mantle. And as it sinks, it allows a gap or a window in this slab where material can upwell, or the hot mantle is drawn towards the surface. And as that mantle, of course, gets drawn towards the surface, it decompresses and it melts. And as it rises, it can mix with material that it goes through, like this accretionary complex, and it can form a slab window volcanic rock. So this is a slab window tectonic setting, where essentially a mid-ocean ridge is overrun by the convergent boundary, and it draws mantle rocks towards the surface where they melt and form volcanic rocks, not a ton, but a few in this very coastal area. Okay, so this makes some sort of interesting predictions. If this model is true for the slab window, then we should be able to see this these slab window volcanics essentially grow with time. Okay, so here we are. This is where the slab window starts about 27 million years ago with the Morro-Islay Volcanic chain. But as time goes on, you'll notice that this zone where that slab window exists grows to the north and then particularly to the south, right? So that by 15 million years ago, there should be a huge section of slab window. So it turns out that there are other volcanic rocks that are in the coastal areas of California. And so in blue here, including the Morros, as well as something called the Cambria felsite, which is a volcanic rock near Cambria. There are some older slab window volcanics. Between 25 and 20 million years ago, you can see here that they shift to the north. And then between 20 and 10 million years ago, there's a big series of eruptions off here in Southern California. So the point here is that as time moved on from about 30 million years ago, the area over which these volcanic rocks could be found in the coastal areas of California, it grew as the San Andreas Fault grew and as that slab window grew. Okay, so let's look at this video one more time. So this is the Farallon plate subducting until about 30 million years ago. And when it does that, what happens is that Farallon plate gets split into two. And now this plate that's in the northern area here, we call the Juan de Fuca plate, which is the plate that's subducting off the coast of Oregon today. And the slab window grows, and as it grows, this is the San Andreas Fault. So the San Andreas Fault essentially initiated when the Morros formed, and that mid-ocean ridge got overgrown or overrun. And moving forward in time here, we really see the development of the Big Bend and the San Andreas Fault. And going all the way to today, we can see the entire San Andreas Fault and then segments of Baja that are being opened and pulled away from mainland Mexico. And this is sort of this transformed segment where we might expect to find some slab window volcanics. Let's go just take a look here in Northern California. And this is a map of Northern California today. So this is the northern end of the San Andreas Fault system. So here's San Francisco. And this is the Gorda plate, which is the southern tip of the Juan de Fuca plate. What you'll notice here is that there are some geothermally active areas, like the Clear Lake volcanics and the geysers. Sutter Buttes is out here in the Great Valley. And these are slab window volcanics at the northern tip of this growing slab window. As soon as you cross this area, now the volcanic rocks go inland, and that's because they're offshore of the subduction zone here, where the Gorda plate and the Juan de Fuca plate are subducting, and that's why we have Lassen Peak and Mount Shasta and the rest of the Cascades that are typical volcanic arc type volcanics. So there's a transition here where we have these coastal volcanics that are associated with the slab window to the more volcanic arcs that are associated with the slab subduction and the wet melting in the mantle that are much different from the slab volcanics here in Northern California. Okay, so there's different types of volcanic settings, different types of rocks forming in California, and this is still going on today. So I think I'm going to leave it at that. I'm about out of time. So here are some of the conclusions. Hopefully know a little bit more about dacite and a little bit more about how the Morros are associated with the growth of the San Andreas Fault. So I'm going to stop there and let people ask any questions.